Problem 1. A heart shape is drawn by constructing semicircles of diameter 1 on two adjacent edges of a unit square, as shown. What is the radius of the smallest circle containing this heart shape? So the radius of that small circle, well, let's first draw that circle. So we know if that circle is the smallest possible circle, then it must be tangent, right, to those two semicircles. And it must also contain this, right? Imagine shrinking a circle all the way down until it's barely touching that heart, right? Then it would be like this. In particular, if we completed this circle, what do we know about this point over here? And, for example, the center of our big circle here. Well, we know that since in any two tangent circles, their centers are collinear with that point of tangency, this center here, which happens to be the midpoint, remember we drew this as a diameter, so the center is the midpoint, is collinear with the other center, the center of the big blue circle, and their intersection point over here. Okay? Similarly, we can say that these are tangent here. So that means that these are lie on line, and by symmetry, we also know that this point lies along the line of symmetry of that square, in the entire heart shape, right? So now that we have this, imagine we call the radius r. Then what happens is that we can calculate this distance here by saying it's the entire distance r, right, the entire radius, minus this length, which, because it's the radius of a semicircle of diameter of 1, must be 1/2. So that means that this length is r minus 1/2. And we can say, for example, since the side length of the square is 1, this whole diagonal from here to here is root 2, meaning that this length is root 2 minus r. And finally, this length here is 1/2, because it's the radius, right? It's also half of our unit square. So this gives us a nice triangle to work with. We also know even that this is a 45-degree angle. So this should be enough information then to compute r, right? We're just filling out the lengths and finding out what's a good triangle to deal with. So now that we have it, let's use the law of cosines. The law of cosines tells us that the square of one side is equal to the sum of the squares of the two other sides, so root 2 minus r all squared, plus 1/2 all squared, minus 2 times the cosine of the angle between the other two sides, 45 degrees. We know that to be root 2 over 2, times the product of the other two sides. And notice that if we expand this out, the quadratic terms will be r squared here and r squared here, so that will cancel, and we know we're on track for a nice solution. So now we calculate r squared minus expanding out, we get r squared minus r plus 1/4 equals r squared minus 2 times root 2 times r plus root 2 squared, 2, plus 1/4 minus, notice that this 2 cancels with this 1/2, so you just end up with root 2 over 2 times root 2 minus r. Root 2 over 2 times root 2 is 1, and that's a plus because the minus cancel out. Root 2 over 2 times r. Now let's cancel out those r squareds. Now we end up with this. We can cancel out those 1/4. So let's bring all the r's terms to the left. So it's minus 2 root 2 becomes plus 2 root 2, plus root 2 over 2 becomes minus root 2 over 2. So we get plus 2 root 2 minus root 2 over 2, and then we also have a minus r here. And then on the right side, we just have plus 2 and minus 1. So that gives us 1. So we just get 3 root 2 over 2 minus 1 all times r is equal to 1. That tells us that r equals 1 over all of this, which equals, well, let's multiply out by 2, top and bottom. And now we can multiply top and bottom by the conjugate just to get rid of that ugly denominator. So it's 3 root 2 plus 2, and then 3 root 2 plus 2. That becomes, well, the bottom becomes 18 minus 4, which is 14. Top becomes 2 times 3 root 2 plus 2, We know that that cancels with that. And we end up with a final answer of 3 root 2 plus 2 all over 7. Final answer.